Alright, this video is on electron configurations, the 3 ways to write electron configurations, and then the 3 rules that govern configurations. And so this stems from after learning about atomic orbitals, the S, the P, the D, and the F, and talking about how we place electrons in in those orbitals. So we'll do the rules first. So the first rule that governs electron configurations is something called the off-ball principle. And basically this is a very simple rule, and it says that electrons occupy the lowest energy orbitals first. Okay, so what that means is that if there's room in the 1s orbital, an electron will go there rather than into the 2s orbital because the 1s is lower in energy. Okay, this is a fairly simple rule to understand. The second rule is called the Pauli exclusion principle, and it says that an orbital can hold a maximum of 2 electrons as long as they have opposite spins. And so this is kind of weird to think about, but the electrons, of course, are moving in an atom and they're spinning. They're either spinning clockwise or counterclockwise, and that's really hard for us to draw. So instead we adopt a model using arrows pointing up and down to show the different spinning direction. And so what this will look like when we get to this part in the drawing is if we were going to draw a 1s orbital, I can put 2 electrons in there, but only if they have opposite spins. And so the way we do this is we the first electron we put in, we draw with an up spinning arrow, and then I can put another electron in that 1s orbital as long as it has a down spinning arrow. Okay, and that is how that works. So 2 electrons can live in the 1s, or 2 electrons can live in any orbital as long as they have opposite spins. Okay, so this is good, but you could never see something like this, okay, because that is no good. Okay, and then the third rule says, the third rule is called Hund's rule. And Hund's rule says for degenerate orbitals, and we talked about degenerate orbitals. Those are orbitals of the same energy, like the 2p orbitals. So for degenerate orbitals, electrons occupy, I'm going to say, this sounds weird, but I'm going to say they occupy single before double. And so what that means is if you had the 2p, I drew 3 lines, right? Remember, because one is lies along the x, one lies along the y, one lies along the z. So and they're all of equal energy. Okay, they're degenerate. So if I had to place 3 electrons in the 2p orbital, well, this rule says that they're going to go in their own orbital before they have to double up. So if I were to place 3, I'd put the first one in the first orbital, and then instead of pairing it, I'd put the second one in the second, and the third in the third. Because everybody has their own room, so to speak. And only if I had to put 4 electrons in, then I would be forced to double up, and I would, of course, spin the opposite way. Okay, so that's what Hund's rule says, that if you have a degenerate set of orbitals, like the 2p, the 3p, the 3d, that they're going to fill single before they fill double. Okay, I always compare it to if you have siblings and you have the option to have your own bedroom, rather than share, most people are going to pick to have their own bedroom. And so electrons do the same thing. They have a single room until they're forced to have a roommate, so to speak, okay? So those are the 3 rules that govern electron configurations, and here's the 3 ways to write electron configurations. However, before we do that, I want to go to the periodic table and look at something real quick. Okay, so Now I can't write on this because it's a photo, but we'll just talk about it. So remember that the periods are the energy levels, okay? So this first period is the first energy level, and the second period is the second energy level, and the third is the third, and so on and so forth. And then remember that this over here is the S block, right? This is the P block, this is the D block, and this is the F block. So we're going to fill starting at the beginning, okay? And so what we're going to do, we don't have to memorize the order of anything, because we know that this first orbital is the 1, and it's an S, right? If you're looking at your table that's colored, it's whatever color you colored S. And then this is the 2, because we're in the second energy level, S, right? And then still the 2P, okay? And then the 3, right? We're in a new row, so the 3S, and the 3, still in the same row, P, and then new row 4S, and then remember here's where life gets a little funny, and this goes to not the 4D but the 3D, and then back to 4P, okay, and then 5S, 4D, 5P. Okay, so keeping that in mind, that is how we're going to go through this. Sorry, I clicked on the wrong thing. To fill or to write these electron configurations. Okay, so you're definitely going to want to have your periodic table out while we're doing this, and I can try to dual screen, maybe. Okay, so the first way is it's just called electron configuration notation. So we'll do a couple examples. So I'm going to do, let's say nitrogen first. Okay, so the way we write this, okay, let me see if I can dual screen here. Let me go back. Oh, I don't know if I can with a photo. Oh, maybe. Oh, okay. Ta-da. Perfect. Okay, so the way we do electron configuration notation is we start at this thing's big though. We start at the very beginning and we talk about the first orbital we encounter, which is the 1s. Okay, so we write down 1s. And then we realize that if we're going all the way to nitrogen, okay, oops, I always forget that I can't. Ugh. If we're going all the way to nitrogen, which is here, okay, then the 1s is full. Oh, that's better. Okay, so if the 1s is full, it holds 1 and 2 electrons, right? All I'm doing is counting. And so, but I'm not to nitrogen yet, so I keep going. So then I encounter the 2s orbital, right? And if I'm going all the way to nitrogen again, the 2s is also full. So I have to proceed through the 2s to get to nitrogen. So 1 and 2. So 2s2, and then the next orbital is the 2p. And all I do is count until I get to nitrogen. So 1 and 2 and 3. So nitrogen's electron configuration is read as 1s2, 2s2, 2p3. And I didn't memorize anything. I'm just following the table. So now let's do, let's do calcium as a second example. Okay, so the way these work is the same every single time we start at the beginning. So see, they're very similar at the beginning. If I'm going to calcium, who's right here, I first go through the 1s, and it is full with 2 electrons, right? Remember, all I'm doing is counting 1 and 2, followed by the 2s, which is full with 2 electrons, followed by the 2p, which is full with 1, 2, 3, 4, 5, 6, followed by the 3s, which is full with 2 electrons, and the 3p, which is full with 6 electrons, and then the 4s, which has 1 and 2. And so that is calcium's electron configuration. Okay, so that's the first way to write electron configurations, and it's just called electron configuration notation. The second one is called an orbital notation or orbital diagram. So I'm going to do the same two as examples. I'm going to do nitrogen and then calcium. So this is where we're actually going to like draw out the orbital. So we're going to do the same thing and progress through the periodic table, but this time drawing the fact of drawing the orbital. So for the first orbital I encounter, of course, is the 1s. So the 1s gets one little line. I label it as the 1s, and then I know that it has 2 electrons in it, 1 and 2, but this is where I represent them as arrows. Okay, so I'm going to do an arrow up and an arrow down, followed by the 2s. So the 2s looks the same, just a line, and it has 2 electrons in it, one spinning up and one spinning down. And then, of course, I get to the 2p. Now, the 2p is going to have 3, right? Remember, because it has 3 orientations that lie along the x, the y, and the z axis. And because I'm stopping with nitrogen, who only has 1, 2, 3 electrons in the 2p, I only need to place 3. And this is going back to that Hund's rule that says they're all going to go in single rooms. So that's what nitrogen's orbital notation would look like, and calcium's, okay, would look kind of similar. So we would first encounter the 1s. We have an up and a down. We have the 2s. We have an up and a down. We have the 2p with 3 orbitals, and we have an up, an up, and an up, and a down, and a down, followed by the 3s with an up and a down, the 3p filled with an up and up and up, a down, a down, a down, and then, of course, last but not least, the 4s, which has an up and a down. So that is the orbital diagram for calcium. And then the third way to write electron configurations is kind of a shortcut. Excuse me, and it's called the noble gas notation or configuration. Okay, and so the way the noble gas configuration works is like this. So I'm going to use calcium as my example in this one. So when I write a noble gas notation, what I do is I find the element I'm talking about, who's calcium, and I go to the noble gas who comes before it on the table, not after. So the noble gas who comes before calcium is argon, and I put argon in brackets, okay? Because what we're essentially saying is that calcium has the same configuration that argon has up to that point, right? Both of them would have 1s2, 2s2, 2p6, 3s2, 3p6, okay? But then calcium keeps going and has 4s2. So we add that on to the noble gas notation. So what we're saying, what we're saying is that calcium has argon's same configuration as argon up until that point, and then it has 2 electrons in the 4s orbital. And so that's the way we do noble gas notation. We go back to the noble gas who comes before, and remember, noble gases are all the way over here, group 18, okay? And then we continue from there. So let's do one more. Let's do like, I don't know. Let's do cadmium, CD. Okay, here he's right here. Right there. All right, so find cadmium. There he is. Noble gas who comes before is going to be krypton. So we put krypton in brackets. And then all we do is we proceed from krypton until we get to cadmium. So this would be the 5s2. And then be careful, the 4d. Let's see, what is that? Is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4d10. Okay, and that would be the noble gas configuration for cadmium. So what might be a good idea is for you to pause this video and to try these practice problems. Okay, and try them on your own with your periodic table, and then play the rest of this video to see if you were correct. right, so here are my answers for these practice problems. So electron configuration for carbon, 1s2, 2s2, 2p2. For vanadium, this one's a little bit longer. So vanadium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. And then iodine, which is tremendously long, is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, that's a 2, 3d10, 4p6, 5s2, 4d10, 5p, what is that, 5p5. Whew. That's a long electron configuration, and that's when you wish I had asked you for noble gas. Okay, orbital diagram for phosphorus. Remember, this is the lines and the arrows. So 1s is full, 2s is full, up, down, followed by the 2p, which is all full, but it fills like this, up, 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 and then down, down, down. The 3s is full, and the 3p is not full. The 3p has 3 electrons, up, up, and up. Manganese, not magnesium, manganese, Mn. So 1s. I'm going to teach you a trick. It's often acceptable to see half arrows here, and that's only because you don't have to lift your pencil, and you can fill them very quickly. So I'm going to switch to that now. So 2s, an up and a down. 2p is full with an up, 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 down, down, down. 3s is full, up and down. 3p is full, up, 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 down, down, down. 4s is full, up, down. And 3d is going to be drawn with 5, because remember there are 5 orientations, and we're counting over 1, 2, 3, 4, and 5. So everybody has an electron. And there you go. That is manganese's orbital notation. Noble gas notation for boron, go back to the previous noble gas who comes before, which is helium, and continue from there. So that would be 2s2, 2p1. Barium, you really wouldn't want to write a whole configuration out for barium, so noble gas is the way to go. So the noble gas who comes before barium is xenon. And then we continue from there, which is very short, which would be 6s2. And then, this should be bromine, sorry. And then bromine, noble gas who comes before bromine is argon. And continuing on after argon, we have the 4s2, 3d10, 4p5. And that is your noble gas notation for bromine.